To start our last lecture, this will be a more relaxed, Saturday and so on. And this lecture is actually kind of example of a simple modeling exercise, which allows me also to introduce a concept that is being talked about in lots of places, which is tipping points, hysteresis, alternative stable state. Depends on which area you are. The name of alternative stable states is used in ecology, and tipping point is more used in climate dynamics. And so, but I will do this with an example, which is the study of the dynamics of vegetation in semi-arid regions. Okay? So here's just a map, and you see that there are lots of regions which are either arid, completely arid, or semi-arid regions in the world. You see, it's quite a lot actually. And so here in Brazil also we have the northeastern region of Brazil. It's called the semi-arid region of Brazil, Sertão. And so, how could we build a model for the quantity of biomass in a given region? Okay? So the first thing is you have to know what's the main limiting factor. Okay? So in semi-arid regions, almost by definition, it is the water. Okay? So water is a limiting factor. So, which is obviously not true in a tropical region where water is abundant here. Okay? So, we want, if we want to, I should start again. Hello. So if we want to build a model describing the dynamics of biomass in a semi-arid region, we have to take into account the quantity of water in the system, right? So, but there will be a kind of feedback loop, okay? Because water coming from rain is absorbed by the biomass, right? So, the biomass, the water induces the growth of vegetation, but the vegetation depletes the water, okay? So let us start with our model. So we'll have essentially two variables which are connected to the biomass and to the water in the soil. Okay, water in soil. And this is like a predator-prey thing. Okay, the prey being the water and the predator being the vegetation, but it's not exactly, because water is not a biotic factor. It's not a living being. It's an abiotic factor, and therefore water does not give birth to water. So we have to make a modification. Okay? So, okay, our two variables therefore will be the amount of water in soil and the vegetation biomass. Okay. Okay, so there's an equation for the amount of water in soil. So the variation in time of the amount of water in soil comes from, there's a positive term, which is precipitation. Okay? So you see that this is not the usual term that we use for biotic resources. A biotic resource would have something, say, dW dt, if it would be proportional to some, say, a constant times the resource. Here, no. There's a certain level. It's like water comes from outside, okay, the system. So there's no really birth term. It's not a Malthusian growth. It's just water being entering the system through rainfall. Well, then you have evaporation, which is a kind of mortality of water in the system, evaporates. Okay. And then it has to be absorbed by vegetation. So you ask me, why this term, Cu square W? Well, this you can do studies for this in a lab. You have water, you have plants, and you see how is the relation between how much water is absorbed per unit time given a certain biomass. Okay? So you can fit a law empirically. So this is an empirical term. It comes from laboratory. It's not the fundamental thing. It comes from laboratory measurements. Okay? So first of all, you see water comes from precipitation, okay? and goes away through absorption and evaporation. Okay? So we are not taking into account, or we are not considering that the precipitation is related to, for instance, the evaporation. You could have a cycle. And this is okay for semi-arid regions. Okay? The amount of water that the rainfall that you have in these regions is not due to the water evaporated in that region. It's usually from elsewhere. So if you are not doing a global model, we are doing a regional model. So it is true for semi-arid regions that the process is not local. It comes from the global circulation. The precipitation comes from global circulation. Okay? This could be challenged if we were talking about tropical regions, okay? Where you have such an amount of evaporation that you could have actually a feedback. The evaporation creates the precipitation. So the evaporation would say it doesn't take the water out of the system. It recycles only the water. But this is it's not true for semi-arid region. Okay? So this is the first equation. So we need the second equation now for the biomass. And well, the biomass is easy. So if there is no water, the biomass has only a natural death rate, okay? Biomass goes away without water. Okay? Well, and then we use the same form as we use for the absorption of water by by the vegetation. We put the same term here, but a different constant, which means kind of efficiency of transforming water into new biomass. Okay. So this is a very simple model. There's are two equations, and for two variables, it's a system of two ordinary differential equations. And now, after 1 week of talking about this kind of systems, we are pretty confident we can do something with that. Okay. So, first of all, non-dimensional variables. Again, if you go back here, how many constants? 5. Okay? 5 parameters. We don't like 5 parameters. We want less parameters. I can rescale the value of the vegetation biomass. I can rescale the amount of water, and I can rescale time. Okay? So I define new variables with capital values, with capital letters here. Is this working? Yeah. With capital letters, and there's this ugly things that E over square root of, where does it come from? Well, this comes from the following. It's just adjusted such that our equations will be simple. That I will get some factors which have a coefficient 1. Okay? So it's, you know, you can arbitrarily scale any variable. Okay? So if you want, you could say, I could write something like that. Some alpha times the old variable, same for the biomass, and the same for the time. I could do this. Alpha, beta, gamma, arbitrary constants. Okay, I think take a new variable, okay, and rescale arbitrarily, and then I can choose alpha, beta, and gamma in such a way that when I plug this into my equations, certain coefficients of the equations will be 1, okay, which makes the system simpler to analyze. So I have 3 arbitrary parameters here, which I can choose in such a way that I will eliminate 3 parameters from the equations, and I will, at the end, have only 2 parameters, okay, which is better. Okay. So, with doing this algebra, we will end up with the system of equations here on the top. You will have only 2 parameters, which are here capital A and capital B. And A is, so B is easy to understand. B is just the ratio of the mortality terms, okay, up there. B is the water evaporation, and D is the mortality of natural mortality of biomass. So this is the ratio, okay? It has no dimension, B. And A is a combination of all the rest of the constant, but what I want to emphasize that A is directly proportional to the capital A is proportional to A, which is, as you remember, here in the top, the small a is the precipitation. It's the amount of water which represents the rainfall in the system. So capital A is a measure of the precipitation, and B is a measure of the balance of the mortality rates. So now I have 2 equations with 2 parameters. What can I do? I go and set points. Okay, I want to know the equilibrium states of water and vegetation. Therefore, I'm looking for the values of vegetation and water in the soil, such that the derivatives are 0, which implies that the right-hand side of the equations have to be 0, which gives me a system of 2 algebraic equations, which are okay. I mean, they're just system of 2 algebraic equations. So can I actually solve this? Yeah, I can solve this system of algebraic equations, and here we go. We have, oh, it's not very good choice of colors. Anyhow, you can see it, yeah. So there's one fixed point the one in the middle, which says that the vegetation is 0 and there's a certain amount of water in the soil. So this is the bare state, complete desert. Okay? There's no vegetation at all. Never. 0 vegetation. But given that this inequality is satisfied, A larger than 2 times B, you have 2 more stable states, which are given, this comes as solution of second order equations, okay? By these values here, okay? So A larger than 2 times B means there has to be enough precipitation, okay? The A, remember, is a measure of the precipitation. So if precipitation is sufficiently large, you can have 2 more stable states. But now, as always, we have to ask ourselves about the stability of these fixed points, and I will just quote the result. I'm not giving you the stability techniques of stability analysis in this school. So if you go for the results, which can be done if you're a mathematician or a physicist or even a biologist that has been trained, more mathematical aspects, it's just the analysis of eigenvalues and Jacobian matrix. It's all more or less simple. And so, okay, before that, okay, that's, okay, this is already what I told you, yeah? So, okay, stability analysis gives you the following results. So, the fixed point width, which represents a desert, which is 0 biomass, is always a fixed point which is stable in any case. So, okay, it is stable, and means that deserts are stable fixed points. We don't like this, yes? If you go to, if you are at the solution 0 biomass, it is stable. You can, if you introduce some biomass, it will die out and go back to the same solution, which is the desert. Okay, so there is kind of resilience of the state, which is the desert. Okay? Well, and the other fixed point, there's one that's always unstable, and then there's one which is stable, provided that B is smaller than 2. Okay? So if B is smaller than 2 and A is larger than 2 times B, then there are 2 fixed points. The desertic fixed point and this other one here. Okay? 2 possible. So for the same set of parameters, I have 2 fixed points. This is called a bistable system. Okay? It's a system that exhibits bistability. We can see this graphically here. So what I am representing here is the following. I'm showing you here the equilibrium biomass in terms of the parameter A, which is the precipitation, okay? So at the point A equal to 2 times B, below, okay, not before. First we have the bare solution, which is 0 biomass, which is always stable here, okay? But in this region, provided that let us consider B smaller than 2, because otherwise there's no, I mean, there's no point of making any analysis. It's just a Zertic system, okay? There is another fixed point which appears here, and, well, if you calculate the value of the biomass, it will be a function like that. So, in this region here, you have Bistability, and here you have on the desertic solution, bare state. So, very good. Now, let us, so you could ask me again, but if I give you an initial state for the equations, where will the ultimate fate of the solution go? I mean, to what value of biomass? Okay? So this will depend on the initial condition. Okay? So taking the case b smaller than 2 and a larger than 2 times b, then you have 2 possibilities. Okay? Depending on the initial condition, you can go to this point here, the fixed point, which represents the vegetation in the system, or you can go for the fixed point where you do not have vegetation at all. Okay? On this region, you can start with any initial condition. You go always to the zero, the fixed point, which is 0 biomass. So now let us make an exercise. And let us consider the following possibility. Let us consider the possibility where the amount of precipitation slowly varies in the system. Okay? Why slowly? Slowly varies is the following. If A is highly variable, I should have put the A as a depending on T in the equations. Okay? And I should have treated the system as a non-autonomous system. Non-autonomous is when some parameter depends on the time. Okay? So we would have a different analysis. We would not even have a fixed point because the system is non-autonomous. But say that the variation of A is slow, such that the system is always in a quasi-stable state. Okay? So it rises very slowly, and the system has time to adjust to the stable state, which is connected to that value of A. So this is clearly for, if you think about now, really desertification situations, it's meaning the precipitation, we are not taking the variation of the precipitation on a daily basis. We are taking kind of situation where the precipitation is variable over large, for a long time, on long time scales, like a century, for instance, something like that, or years, tens of years. Okay, so that's what we want to see. Now, say that you live happily in with vegetation cover, and you're okay, everything is nice. It has say you are here at the start. There's a certain amount of precipitation here corresponding to this value, and you are in this situation. Okay, and now let's say that there's a climatic change, or natural climatic change. I'm not talking climate change. There's a variation, and then say you are decreasing A. So as it slowly varies, the vegetation cover will also be variable and will follow the A. So you are here, then you are here, and then here, and here, and here. But when you get to this point here, you still have a lot of vegetation here, okay? But once you pass this point here, you go to 0 directly. It's only pixel point. And when I say directly, obviously this is a process, which is a transient, but your stable fixed point is the 0 vegetation. So you see, you don't approach continuously the 0 here. I mean, in fact, well, you will approach continuously, but the stable fixed point is not, it's not continuously here connected to the 0. You have a highly high vegetation cover, and then in a process that is quite quick, you get to the 0. But now, suppose that climate change and climate variability induces an increase of water, of rainfall. Then you go back here. But this fixed point is stable. And even if you go back to your starting point, you will be on the 0 here. Okay? So this is called in physics and hysteresis. You have a loop, you have a continuous change on A, which is a cycle. So A decreases and later on increases, but you don't get back to the previous state. There is a new state here, which is the desertification situation. So that's something which is important, because you see, if you go to a situation where you have desertification, you cannot go back to a situation where you have vegetation cover, obviously, unless you are able to introduce a very large perturbation of the system, which kicks you to this point again. Hysteresy. Oh. So it is, yeah, it is. But it's not a natural process, okay? In Israel, they do this. You have to have a lot of plants, but I mean, this model is still very simple. It's not exactly like that, okay? But there is, the desertic situation is resilient. I mean, small perturbation don't take you away from the desert. Well, if you can induce perturbations through vegetation, introducing vegetation, and so soil treatment and more water. Okay, and this can make the desert flourish. But actually, this is done as long as I know. Well, this is done in Israel. Okay, but there's no, and it's also not. It's a small scale. Yeah, I mean, it's not the whole. You won't make the Sahara flourish. Okay, biome. It's not. So good. So. This shows you that there is a stability of the desertic situation, and therefore you are quite interested in not going through this point. So mainly people from who work in climate dynamics and climate change and so on, they call this a tipping point. Okay? In ecology, usually you say that these two fixed points are alternative stable states. And in physics, you say the system exhibits bistability. Okay? So the jargon depends a little bit on the subject that you are actually studying. Okay? So now, okay, this is just a cartoon of what I just explained to you. But you can ask it, is it true that this happens, okay? So, and here are the glory of this model, the big glory. This is estimated vegetation cover of the region of Sahara over a very long time span. Okay, this is done by examining pollen in the soil. Okay. And you see that there was a higher vegetation until the year more or less 6,000 before present era. And it kind of collapsed very quickly in less than 1,000 years, in about, well, say, 300, 400 years, from something which has a vegetation cover and something that has a very small vegetation cover. Okay? So this is an indication that actually we had a region with biomass which collapsed. Okay? Well, you could ask me also, well, couldn't there be some alternative explanation? Yeah, there could be. Okay, you know, so not be a collapse due to bistability, but well, this theory can explain this situation. Okay, it explains also you don't hear about deserts becoming covered with vegetation naturally. Okay, that's not the usual thing. Okay, we have they presently have a very large region undergoing desertification, which is the Sahel. This is just south of Sahara. And you don't hear about, okay, now that's new trees. You see that this is vegetation. And if you look for deserts in the world, they are not, poof, oh, lots of trees. You don't see this. Okay, so there is the reason to think that, well, something like this is actually taking place there. Okay? So, glory, but there's always a misery, okay? Always a misery, and well, this model is too simple because it has something like, okay, the transition which happens here in this model takes you to a situation where the vegetation goes to zero. Okay? Well, we know that deserts, except some special, well, region of the Sahara and in the south of Africa and the region of Namibia and also the Gobi Desert and so on, certain parts of this region, there are remnants of vegetation, okay, kind of shrubs, okay, not really trees. There is some vegetation that remains there. So we would expect in a more realistic situation that your desert here is something different from zero. But a more serious problem would be, okay, if the real driver for the vegetation is the water, you'd expect that if there's a large enough amount of water, we could have again, vegetation. So this means that in this model, it seems a little bit weird that even if I go for very large values of A, I'm still always with the desertic solution, the bare solution. It's always stable even if there's a deluge, even if it rains catastrophically, well, even in this case, it's stable. Okay? So you can build better models. Okay? This model is actually too simple to capture this kind of features. And one thing that you could be interested in doing is also there's water that is not uniformly distributed in soil. That's the soil near the surface, and then you have lower soil. This water does not actually evaporate. Okay, so you have to take into account more physical phenomena which participate in this kind of dynamics, and you can do better models. And the people actually, that's an area of research. People presently still study this kind of thing. This is just one model, and by the way, it's called the Klaus-Meyer model, and can be improved. So if you improve it, you get something like this. You get a situation where you have two tipping points. Okay? You have a region of fixed points here, and here these are unstable fixed points, but there's still a new value of A here, such that this is not anymore stable. Okay? Then you have this region and this here, which is the bistable region, the Bistability region. Here you have a desertic situation. Here you have, again, vegetation cover in this region. Okay, meaning that if the precipitation is large enough, you can go for that back. Therefore, you say, I started here and I went here and I get back to this point. Still true. But if I cross this critical point, I can go back to non-desertic situation. Huh? So this is more realistic, okay? Meaning that, but usually this does not happen naturally, as I was telling you. It happens more if, for instance, this means that if I go here, it means that irrigation can help me, okay? So this is mean irrigation, and artificially increasing A can work, okay? And still, if you do something still better, you have something like that, okay? You have a non-zero, you have a very low value for the biomass and a larger value for the biomass, but it's not zero, okay? So these are models with many more equations. I won't write down the model, but you can expect something like that. No, the line in the middle is just plotting the unstable fixed points. Okay. It has 3 fixed points, but one of them is unstable. It's only the upper one and the lower one that are stable. In the middle is an unstable. No, there's no zero solution in this case. Okay. This is a case where you have always some vegetation. This would be a more realistic situation for. This one I actually don't remember. It's a bunch of equations. I can't remember now. But this goes usually through really looking how water is absorbed and how the dynamics of water in the soil happens. Okay. So you have regions of the soil, and because here we say just water evaporates, but well, sometimes it also flows. Okay, you have lots of things that happen there. So I'm not a specialist on vegetation, and this is just taken as an example from just looking at the plot. Okay. Well, so this is the big view, the big picture of how you have desertification. But why I'm talking about desertification? Because this allows me here in a very simple model to introduce the concept of bistability, having more than one fixed point, and the concept that I can have more than fixed points, but when I have a region where I have only one fixed point and a region where I have two fixed points, I can have this phenomenon of hysteresys. Okay? So, the question that you would like to answer, and which is still very debated, how can I know that I am close to a tipping point? Say I'm here, or here, or here. How can I know that, oh, danger? Is it possible to have early warning signals of the transition? Is it possible? Okay. So this is a long story. Okay. In the particular case of desertification, we actually have something, but as I will explain, it's not to be it's not something that you can use in general for other systems. And this is the following. Desertification also has a spatial aspect, okay? Here we have just taken the region and the biomass and the amount of precipitation. But actually, you can take photo and see how the vegetation is distributed. Okay? Then usually what you have, if you are on this kind of plot here, okay, is that in this region where you are kind of safe, if you take a photo, you get fully covered region. Okay? But as you progress in this towards the tipping point, you will get patterns of vegetation. For instance, stripes. And if you are very near to this point here, you get spots. So this is taking a photo, aerial photo of the region, and looking not only at the total biomass, but at the distribution of the biomass in the system. So if you do this, you will have a sequence of different patterns in the system, and then you will know that you are closer or not, if you are close or not to the tipping point. So this is, well, if you can, yeah. Mm-hmm. Yeah. Yeah. Yeah, he is more regular. Okay, here it's not so much noisy things. It's pattern formation really from like Turing patterns, and this it's coming from, well, from I think microscopically really it's diffusion processes here. Okay. So this is a kind of solution to know this thing. But now, all this formulation here, you can think that there are many systems where I can have this kind of alternative stable states, where I can have more than one possibility, and you have two stable states, certain system, for the same parameters. Classical example is lake eutrophication. Okay? Lake eutrophication is something that everybody has seen probably. You have a clear water lake, and then you get water lake which is kind of green, full of algae and so on. So what drives this is nutrient supply. So if you have too much nutrients, you get very high number of algae and or other kind of aquatic plants, because there's so much nutrients, and actually, well, then the fauna dies out and so on. And this is also described by a system which has stable, alternative stable states. And nutrients in this case, where do they come from? Usually it's kind of pollution. Pollution is nutrients for algae. Okay? So this is typically if you have a lake and then you have near, say, agricultural land, and then there's some flow of something that has a lot of usually it's problem with the phosphorus and nitrogen and this kind of thing, too much nutrients. Okay? So the eutrophication of lakes, it's also a system which has this, but this happens on a very shortest time scales than desertification, sure, okay? And you cannot look for this kind of patterns, okay? Because this happens in a week, right? There is no way. So in this case, you would also say, okay, I would like to know if the amount of nutrients I'm supplying, because the lake is there and it's clear, is it close or not to a tipping point? Okay, open problem, right? Open problem. There are many attempts and there are many papers on early warning signals of critical transitions. There are lots of things. But the fact is that although there has been a lot of activity in this, all results are such that, well, you can detect the transition, even if sometimes your system is not visual, you just cannot look at it, okay? You can detect through certain measurements the transition, and but it's the transition, it's not before the transition, okay? So you almost get it before, but what you really, because what the practical problem is, I want to stop it, okay? I want to stop it, and but usually you can only detect when it's already taking place. Lakes or yeah. Oh, yeah. Well, I mean, probably you are not able to do this in a short time scale, yeah. No, I mean, when you decrease the size, you mean that you are have a higher concentration. Yeah, diminish the lake. Yeah, I mean, this is for all kinds of. I mean, yeah, but in principle, this is for all sizes. But I mean, if you have an enormous lake, it's difficult to pollute it to the point that it will go to eutrophication. So it's usually smaller lakes. Yeah, in practice, you will not have the enormous lake, all of it eutrophicated, because, well, the amount of pollution would have to be enormous. Yeah. So there's a whole area of early warning signals. It's actually very interesting. It's looking at the system under noise and then calculating autocorrelation functions. Autocorrelation functions, step one, have a peak at this point. Okay, this is for people that know stochastic dynamics. Okay, that's a way to detect it. Yeah, and yeah, there are systems that sometimes actually. Here, this scenario here is a completely deterministic scenario. Okay, I'm not talking noise here. Okay, but there are systems where you can have transitions between stable points induced by noise. Okay, So one example, which is a kind of example that's not biological, is just consider what people call a double well. This is, and consider you have a ball that can go here, okay, under gravity. Yeah, okay. So you have this fixed point and this fixed point. The ball can be at the bottom of one of the wells. But now, say I'm randomly kicking the ball, okay, with a certain distribution. Then it will be here and here and here and here and here and here and here. Well, if you wait long enough, there could be the case that the kick on the ball is strong enough that it goes for this one, okay? And then you will be here all the time, okay? So if you record the position of the ball with a certain time interval, you can you can draw a distribution of positions of the ball, okay? And this, in this case, would give you a distribution which is like this. Has two peaks, okay? This is the typical distribution of a bistable system under the action of noise. And obviously the number of transitions will depend on the height. Yeah, you can break the symmetry, yeah. Yeah, exactly, yeah. You can play with that. Okay. This is symmetric case, but I mean, you can put one above, one, yeah. So, yeah. So this would be a noise-induced transition in systems, okay? And that can actually happen in certain systems. So the final comment is, this is being now a topic which, of much interest in the idea of having transitions between fixed points, between stable states, and their noise or external perturbations, okay? Not necessarily noisy, no? Change of parameters and so on. And one area of research that this has been now debated very much, and there's no final conclusion, is climate change, actually. So you can, if you Google climate change tipping points, you get hundreds of citations. It's actually, you should better look on Google Scholar, because you will get usually only the first 100 results of your Google search will be newspapers or whatever. Climate denial sites. So, but it is a very important thing that people debate if there are really tipping points. But there is also some conceptual confusion, okay? Because you'd say, for instance, people say, okay, there are situations where maybe we have a very strong, a very important transition. For instance, if I have a heat up the Earth and Greenland goes away, okay? And not Greenland, the ice of Greenland goes away. But, well, is it a tipping point? Well, don't know, because it's not necessarily you have two different fixed points. It's just you have heat it up, and then if you cool it down, could be back. So interrogation. Okay, so question mark. So not all transition that seems bad, okay, are necessarily connected to alternative stable states. But well, a lot of people have now doing research in climate dynamics, and climate dynamics is really a difficult subject, okay? Because you need a model for climate. And actually, you don't want a cartoon model. You want a model for climate of the Earth, with everything you have the right to have. I mean, vegetation, with the incidence of light, the albedo, and the atmosphere circulating in the oceans, everything. You want everything. So there are those big, there are kind of 3 or 4 models that compete or in the world, which are monsters. Okay, a person can work for a whole life on this model. Okay? And so, but as they are so involved, it's difficult to see if there are alternative stable state or whatever. Can you explore the scenarios? It's difficult also. Okay. So that's an area that it's actually fascinating for research also, looking for this kind of situation in real systems. What is Binder coefficient? Ah, for phase confusion. Well, you can ask, is this a phase transition? Okay. I don't know if it's a phase transition actually. Yeah, well, you have hysteresis in magnetism, yeah, you could say. But because I mean, this means that you should have a microscopic model behind this. Okay, so yeah, that's why it's called hysteresis. Yeah. So, well, 1 hour, it's over. Well, soft. But now I have announcements, okay? Important announcements. So, these are announcements that I have made yesterday, but I will emphasize them again, okay? And not everybody was present when I was with the groups. It's, well, for tomorrow. We will start 9:30, not at 10 as it is written on the program. 9:30, but we will start really at 9:30. So you will have 20 minutes for your presentation. 20. 20 is not 21. And then after your presentation, you have 15 minutes for discussion of your project. Right. Everybody discussing, okay? So you have a time slot of 35 minutes, okay? So, and the next thing is, we want you to bring your presentations before 9:30. All groups, even if you are the group presenting at 5 o'clock in the afternoon, you want the presentations here at 9:30 on this computer here, okay? Which is the computer that the Institute's computer, okay? So, but in order to start 9:30, we need you to be here, at least one element, one person of the group, being here before 9:30. So one person has to be here between 9 and 9:20, okay? To upload upload any system, but usually it's with a pen drive. Your model here, your presentation here, and test it. Test it is more. If it's a PowerPoint, it's better to test, okay? Because PowerPoint is. We prefer PDF, but I mean you are free to use whatever you want. Not whatever you want, PowerPoint if you want. It depends on what is on this computer, but you can use also PowerPoint, okay? But if you use PowerPoint, look the configuration if it's not bluff completely out of, no? Because, well, we want to be really ready at 9:30, okay? So the idea is also that you will actually pay attention to the presentations and not be working on your presentation during the other people are talking here, while other people are talking. So, okay, so this is the announcement. So have a good afternoon for your work. As I told you, if you need to stay longer, you can stay. And also people asked me if they are ready, they can upload the presentation here tonight or in afternoon. When you're ready, you can come. You can come here if you don't need the night to work on it. So yeah, that's it actually. Good. So good work. There's one point. It seems that the lecture room number 3 is taken. There's some activity. So if you go down and the lecture room number 3 and you see people there, it's well, they can be there. So and this should be from 10 to 1 p.m. So after 1 p.m. it's again it's free. Okay. So I'm not sure this is actually taking place, but I'm been told that to pay attention to this. Okay. So find another place to work. Thank you.